Hi, my name is Josh McGrath. I'm the Soil Management Extension Specialist at the University of Kentucky. I've been asked to cover enhanced efficiency fertilizers in the context of crop management and ecosystem services. I know many of you in the audience, but I've been asked to kind of give an introduction to my background, which will contextualize my viewpoint on some of these issues that we're going to cover today. So my undergraduate was unconventional. It was a split between the Department of Earth and Planetary Sciences and the Department of Geography and Environmental Engineering at Johns Hopkins. What this means is I had a focus on ecology, geography, geology, and engineering. At the University of Delaware, I looked at runoff and nutrient runoff and poultry litter. And then I took a hard turn at Virginia Tech for a postdoc and looked at forest restoration potential of strip mines using Landsat imagery. And so big landscape kind of modeling. Then in 2006, I started at the University of Maryland as the Soil Fertility and Nutrient Management Extension Specialist with a focus on Chesapeake Bay water quality. And now at the University of Kentucky since 2014, I've taken an increased focus on precision nutrient management, which I'm going to lean into heavily today. So nutrient recommendations are empirical models. And so our fertility recommendations, an empirical model, for example, could be we go out to a field, we do 7 nitrogen rates in one field 1 year, figure out which one is the optimum. But if we apply that across other fields or other sites, we're going to be way off. And so we do it across a lot of sites over a lot of years, and we come up with really good average recommendations. So our current nutrient recommendations look like this. On average, they're right, but in every site in every year, they're wrong. Now, there are some mechanistic components. There's a spectrum for sure. But, we need to move towards these more mechanistic or process-based approaches if we want to increase precision. And back in the 60s, this is exactly what George Stanford advocated for, and what we now talk about is Stanford's equation. It's been maligned recently in some of the press, but I think that comes from kind of a misrepresentation of what they were shooting for. And simply, he said that the fertilizer requirement is proportional to the plant requirement, the internal plant requirement, minus what the soil gives it, divided by the efficiency of the fertilizer. And so you're balancing plant requirement with soil and fertilizer supply and subtracting out what's lost. So implicit in all of our recommendations is loss. So there's some environmental impact even when you're following recommendations. Here's some data from Frank Cole at the University of Maryland, and it shows a nitrogen response curve with yield on the left, and he collected 1 meter soil samples post-harvest to look at residual soil nitrate to get that soil nitrate curve versus nitrogen rate. And what you see is a diminishing return function where the economic optimum yield was 173 bushels, and the agronomic optimum yield, maximum yield, was 174. But because it's a diminishing return function, that last bushel took 25 pounds per acre of nitrogen, which didn't pay for itself. So the economic and agronomic optimum yields or rates are very different. So they're kind of in conflict. So this performance objective, when we talk about the right rate and the 4 R's, becomes very important. And then also we notice that we're right here on this threshold where environmental impact starts going up a lot. In this case, that last bushel costs 25 pounds of nitrogen, but 17 pounds increase in the soil nitrate post-harvest. So a potential big environmental impact even when we're in the economic optimum. And this isn't detectable at the farm gate because, that going from economic to agronomic optimum was a $5 per acre loss. If you cut rate, the loss would be much greater. In fact, economists, there's been some papers written using stochastic risk assessment that says the right rate is 30 pounds over the economic optimum nitrogen rate to offset that risk over many years. So cutting rate would provide a public benefit in regards to water quality, but at a private cost to the farmer. So there's this conflict between public benefit and private costs. And when we go into enhanced efficiency fertilizers, the return on investment in those products is very site and time specific. For example, applying NBPT and then having a rain the same day would kind of mute the effect or benefit of that NBPT. So it's like buying a lottery ticket. And so it's dependent on what's the degree of response and how often does that response occur. So when they work, they'll move that economic optimum nitrogen rate to the left and we'll be able to maintain the same yield. But you need to first optimize rate, placement, and timing before moving in EEFs. However, they may have a role in kind of global nutrient use efficiency, this public benefit. And modelers, I think we have enough data that modelers could look at what would happen if we put a nitrification inhibitor in all nitrogen used in North America. Would there be enough public benefit to support that public investment? Because I don't think at the farm gate there is the private benefit. There's There's artificial demand, but not derived demand. And that comes from some support programs and marketing, and also farmers wanting to do better. So moving forward, how do we understand mechanisms? How do we find out what we don't know and interact with these landscape processes to do better and be more precise? Historically, I see a lot of proposals that say we need more data. And so we see all these nutrient response studies that are very conventional, but we don't need more data. We need different data. And we've taken a stab at that with some friends of ours at ARS and Virginia Tech and Oklahoma State. In regards to phosphorus, it looks like this. We try and reduce the plot size to limit in-plot variability. So we have these 40-foot by 40-foot plots with 4 subplots. 2 of those strips are going to get phosphorus, 2 don't get phosphorus. We're just looking at response, and then we shotgun them across the landscape to look at that variability across the landscape in response, the difference between 0 phosphorus and 60 pounds per acre in this case. In nitrogen, we set up a bunch of different nitrogen rates, but our subplot design is a 4-way factorial of starter and side dress, starter and no side dress, no starter but with side dress, starter only for all of those nitrogen rates. So there's 57 nitrogen rates. Every plot looks like this. So we have a zero-end check in every spot in the field, and we can look at the spatial distribution in nitrogen response. And so here's an image of me harvesting one of those plots this October, and it's big. There's over 1,600 plots on this site because the farmer wanted to look at cover crops. So we have a rye cover crop, a rye clover, and no cover crop out there. And really harvest is the limiting factor. I'm doing that with a 2-row plot combine. It takes a full week to harvest that one site. But the kind of data that this study gives us is it allows us, first of all, to come up with a pretty robust empirical recommendation. So we found after a few years and many sites that we need about 250 pounds per acre of nitrogen on average to optimize economics. But that kind of undersells the complexity of the system. And so by looking at response across the site, we see that there's lots of variability. On the left there, we see yield response as a quadratic plateau. On the right, a quadratic model for economic return. And we can start teasing out cover crop, management, timing, and all of these things and figure out a more mechanistic model. In our case, we're using sensors, active optical sensors, to generate an algorithm that changes the nitrogen rate in real time as we travel across the field performing side dress. On the phosphorus side of things, on average soil test work. So when we were below soil test critical level that the University of Kentucky says you need phosphorus, it turns out that we got a mean corn yield response that paid for the phosphorus investment. So on average, if I'm flat rating that field, following soil tests would have paid off. But what's interesting is that 50% of the time, soil test failed. So what's that mean? Each of these dots is a plot, one of those combinations of 4 subplots in 2016, 2018 at 2 sites. And that red line is below that. We say we need phosphorus, but if we're above the blue line, we didn't have a response. And so only half the plots responded to fertilizer phosphorus, but they responded to a degree that they paid for the whole field, in effect. But precision ag, when we just use soil test P as an input in our empirical model, it doesn't work. So what are the factors? Well, one of the things is as yield potential increased, fertilizer response decreased. And we saw this in the nitrogen study too. Landscape position has a strong relationship to this. We think perhaps soil depth, slope, elevation, all of these factors, and with phosphorus specifically, we think total root length is a contributing factor. So if we can have a model that uses potential rooting length and soil tests, we may be able to become more precise in where we assign our fertilizer. In nitrogen, we saw the same trends. When I harvested that field that I showed in the picture, we had plots that got 300 bushels per acre with nitrogen and without nitrogen right next to each other. Across the field, I got 300 bushels per acre with nitrogen and only 120 without nitrogen. So responsiveness varied in space. These processes are the same ones that are involved in environmental models. And so we really need to bridge across these disciplines and bring environmental process landscape models into our agronomic recommendations to create more process-oriented recommendations that they're going to be data intensive, but we have that capability now on farm. And we have to be cautious though, because we can end up with improperly parameterized models that we could have high precision but very low accuracy. We need to consider precision across a range of conservation tools like EEFs to adjust for temporal, spatial, and management variability. But we also need to bring in that human component to understand bias in decision-making and adoption of practices and what are the economic drivers, because that human bias isn't always driven by economics. They're somewhat independent. So that's just some ideas that I hope will spur some conversation and in our discussion. So I thank you for your time. And here's my contact information. Again, outside of this workshop, if you'd like to reach out to me, I'm always happy to discuss these ideas.